Hello everyone, welcome to ETH Online. I'm Pratik and I'm a researcher at Marlin. At Marlin, we work on network layer optimization for Web3. In this presentation, I'm going to introduce you to Marlin Cache, a simple API that speeds up blockchain queries. We'll begin the presentation with a short intro to the current state of dApp ecosystem, issues with it, and what can be done better, and how does Marlin Cache help. We'll also look at how exactly does the cache work and how you as a developer can use it to decrease query latencies for your application. We hope that you will find it super easy to get started with Marlin Cache. At the end of the workshop, we'll look at the prizes which are up for grabs as part of the hackathon for projects using the cache. So let's get started. In recent times, Ethereum has seen an explosion in the number of dApps as well as the users of such dApps. And if you look at the summary below, there are some interesting observations. For one, most of the users are new to the ecosystem. And secondly, DeFi related dApps account for around 97.5% of the total activity. An implication of these statistics is that dApp developers are having to work hard to improve user experiences. Long gone are the days when users had to directly interact with complex smart contracts. High stake transactions can now be made using simple web interfaces which resemble Web 2 experiences. And this is very essential as we transition from early adopters to mass traction. Users now need little to no knowledge of blockchains to use these dApps. However, these interfaces only act as a proxy to connect to a blockchain and present data in a simplistic way. The data presented in these UIs should still come from the blockchain. So, how do developers retrieve data from the blockchains? They might either run a full node or archive node as per the requirements of their application. But running a node reliably so that there are no disruptions for users is hard and resource intensive. Alternatively, centralized services like Infura and Alchemy provide reliable infrastructure to obtain blockchain data for dApps so that devs can concentrate on building dApps rather than running the infra. In recent times, decentralized networks like the Graph are trying to make data extraction even more easier for dApp developers by supporting custom indices tailored to each dApp. However, these services, centralized or decentralized, are still required to operate a full node. If that is the case, what exactly is the problem we are solving? So, the requirement of operating full nodes to support blockchain queries places performance overheads. For instance, take this host with a 145 Mbps downlink. It still takes more than 10.5 seconds for it to load uniswap.info. And a large part of the delay is attributable to API calls it makes to Graph's servers, each of which take 300 milliseconds or more to respond. These delays have implications. Users are fine with such delays today as they consider themselves early adopters. But these might not work as more retail users who are accustomed to Web 2 try these services. As you can see here, page load times have a strong correlation with bounce rates. If the load time increases from 1 second to 10 seconds, then the probability of user bounce increases by about 123%, which is very high. So what's the primary cause of such delays that are higher than 300 milliseconds? The response times are high because currently Graph operates centralized services due to which the latency between the host and the server is high due to the geographical separation between them. Also, Graph node has to run a query on the DB to get the information to be sent to the user. The closer the client is to the server, the lower the latency. But the experience of users is not uniform and worse for users from faraway regions. Decentralization of these nodes can bring indexers close to the users, thus decreasing latency. Indexer nodes, by the way, in graph are the ones that respond to queries on a subgraph data for DI. High resource requirements of graph indexer nodes limit the number of locations that a node can be placed in. Graph's indexer node need to run a archive node to query most famous subgraphs, which puts a heavy resource requirement on running an indexer node. So the barrier to entry for an indexer is high, which in itself is a reason why graphs indexer nodes can't be very highly distributed to make these latencies go away significantly. It is evident from our measurements of the current testnet that the graphs nodes are not very distributed, as most of them run on Hesner online services and mostly out of Germany. So how do we do better? How can we solve these issues? Instead of resource intensive indexer nodes, a low resource node which stores the responses to frequent queries and responds directly when the same query is made can scale better. These can decrease the load on the indexer nodes as well as improve the latencies for the users. Data is updated only once in a block time, so about 15 seconds in case of Ethereum, which is a large enough time that caching is more efficient than querying the DB for data for every request. These nodes can be widely distributed across the world due to their low resource constraints. These types of nodes which store responses to frequent queries and respond directly thereafter are called caches. Cache nodes that are significantly distributed across the world are called CDNs. CDNs today solve a similar problem in Web 2, and Marlin Cache is an attempt to solve these issues in the Web 3 world. What is Marlin Cache? Marlin Cache is based on a simple observation that most of the user activity is from a very few DApps. We can see from the screenshot below that Uniswap, which is the most used DApp by users, accounts for 287k users, while the MakerDAO in 14th position accounts for just 9k users. So a large portion of users access very small number of dApps. Marlin Cache is an event-driven caching system, which means that the data that is cached is only updated once in a block, and some of the cached data can be directly updated by Marlin Cache itself based on the block information without querying the source again for the data. So how exactly does a cache work? When a user sends a request, Marlin Cache requests data from the source, caches the responses. If another user requests the same data, which is very frequent as most of the users use the same interfaces to interact with DApps, the cache data is served to the users. Cache updates the cache data by querying frequently requested data from the source when cache knows that the data is updated. Mostly this happens when a new block event is received. These pre-filled responses are provided when the same query is made, which reduces the latency for the users. Some of the cached data can be updated without requesting data from the source based on the block information received from the blockchain network. This will further improve the consistency of cache with the current blockchain network state. We ensure that the data within a cache is consistent and corresponds to a single blockchain state. Let's take a look at the demo. Uh, so in this demo, we are going to show how Marlin Cache can help in decreasing the query latencies for graph queries. We have used a modified version of the Uniswap Info website for the demo. In the Uniswap Info app, we have changed the query URLs to use a local Marlin cache, which is the most optimum for the page to load, and also a remote Marlin cache with which we are able to decrease latencies as well. We have compared these with, with the latencies for loading page when Graph APIs was used. So let's get started. So this is the page for Uniswap Info website with Graph URLs, Graph API URLs. So let's reload and see how long it takes to load. Uh, yeah, so it took around 8.55 seconds to load, out of which 1.8 seconds was DOM content loaded. So basically, it required the for page to load, it required around 1.8 seconds. So the net comes around 6.7 seconds for the page to actually load. So let's reload it a few times to ensure that this is consistent. Okay, so it took around in the second time it took around what around 8 seconds, 8 seconds to load, and let's reload a couple of times again. Yeah. So as you can see, now it's around 7 seconds, 7.1. So let's stick around 7 seconds because yeah, it's around 7 seconds it takes to load Uniswap website with Graph APIs. Now, on the same machine, let's also look at how Marlin local cache works for loading URL, sorry, for loading Uniswap website. So in this, for this version of Uniswap info, we have just changed the URL for query request to local Marlin cache, which is running on my local system. So let's reload and check. So this is the first time I'm loading. So it takes a while to actually cache the content, and it will generally take more than the time it takes for the Graph API to load. As we can see, it took around 12.5 seconds for the first time to load. But from the second time on, the cache kicks in and makes these load times much shorter. So you can see that now it's less than 5 seconds. So it's around 4.8 seconds to load the page. And if we do it, so it's probably because the block also has changed between the reloads. But if the block is the same, like if we are querying at the same block and a new block is not produced in Ethereum, the query times will be much faster because we don't need to get the data again from Uniswap rather than sorry, from the graph servers, rather than we can load it right away from the local cache. As you can see, some of the queries are still taking longer because they are being fetched from the cache is being updated, and it takes time when that happens. Okay, so now let's check this out. Yeah, so you can see that the load time now is somewhere around 2.87 seconds for the page to load, and this is consistent in general. So just the block times have increased, so the block has changed, so the content load time has also changed. So you can see that it's again around 2.8 second. So you can see that the local cache consistently takes around 2.8 second, which is the optimal, and probably it takes, I mean, even the query latencies are in less than 10 millisecond in general. Sometimes they go up to 20 millisecond, but generally they are pretty less when compared to the graph's actual queries, like the queries which are sent to Graph API, which take somewhere around 300 millisecond on an average they take around 300 millisecond to actually respond. So let's also look at another version of Uniswap Info website where we have used the query URL of a remote cache that is slightly far away from the local machine, right? So in this case, when we load the page for the first time, obviously this has to be cached and it will take significantly higher time. So yeah, so it took around still loading. Yeah, it took around around 12 seconds to actually load, 12.8 seconds to load the page. And from the second time on, like when the cache is already loaded, yeah, it takes lesser time, much lesser time when compared to what it took. So it took around 4 seconds, like 3.9 second to actually load the page. And if we look at this for some more time, I mean, if we do a couple of more reloads and if we make sure that the block is not changing, then the query times will come down even lower. Yeah. So when the block changes, obviously the request has to be sent again, because of which the query times are in general higher. Yeah, so now the block has changed and most of the requests have to be requeried, because of which the load times were much higher. And this is another instance when most of the queries were cached and it took around around 4 seconds to actually load the page. So as we can see that most of the queries, so again the same, like around 4 seconds. So as you can see, the latency for querying the data, given all the static assets for the page are already cached in memory, is around 4 seconds for a remote cache which is slightly far away from the client machine. And also the local Marlin cache is takes around 2.8 seconds, which is probably our target which we want to achieve, to make sure that the query latencies are as if the cache is located right at the server. This will only happen once the Marlin cache is distributed enough that it is close enough for most of the users. And if you look at Graph API servers, it takes around 8 seconds. And cache, I mean, when you compare it to the baseline, which is around 2.8 seconds, which is the minimum time it took for us to load even from a local Marlin cache. You can see that the query latencies are quite different for each of them, and it's around 300 seconds here, in a few milliseconds, like around 10 millisecond here, and here they are around 80 milliseconds, 70, 60, 50. So it's around 50, 60, I guess, milliseconds to actually query the data from a remote cache. So we can see that the query latencies of the requests have significantly dropped, and also the amount of extra time it takes when compared to a local Marlin cache. The Marlin cache is around 1 second. It takes one more second to actually load the page when compared to a graph server, which takes around 5 seconds to actually load. So Marlin cache performs much better in this case. Okay, now that we have seen how fast Marlin cache is, let's look at how you can integrate it with your existing applications. So we currently support caching for Infura and the Graph. We'll see next how easy it is to integrate with each of these services. Let's get started with how to integrate Infura's cache with your application. Infura needs a project ID to accept requests. This project ID can be easily created by creating a project in Infura dashboard. As we are a caching layer and store only frequently queried data, sometimes the queries might miss the cache, and in such cases, requests have to be redirected to Infura to get the response for the query. So we need Infura's project key to integrate with Marlin's cache. In the Infura dashboard, you can find the project ID in the settings section of the project created. You can copy the project ID from here, and now you are ready to integrate with Marlin's cache. You can select a network to get the data from. Then the project ID that you have obtained from the Infura can be added to the cache URL of the network selected to obtain the cache endpoint. You can find the cache URLs for each of the networks in our documentation. This cache endpoint can be used as a drop-in replacement to Infura's URL to use in any of the tools like Web3 and Curl. That's all. You are all set to use Marlin's cache for Infura to decrease latencies for your applications. Now let's look at how a developer can integrate their application with Marlin's graph cache. First, select the subgraph you want to query. Then go to the Graph Explorer on Graph's website and open the Explorer page for the selected subgraph. I have opened ENS here in the screenshot, and you can see that your selected subgraph also will have query URL, which is /subgraph/name/ens domain/ens in this case. Copy the query path to the selected subgraph from here. Now that you have the query URL ready, append that to the Marlin graph cache URL to get the cached query endpoint for your subgraph. Use this endpoint to send the queries, and this is a drop-in replacement for the Graph API endpoint in your application. That's all, and you have now integrated with Marlin's cache for Graph, and you can see improvement in user experiences due to reduced latencies. Any project that you are building, be it DeFi or NFT, can use Marlin Cache to better the UX. Implementing doesn't take more than a few minutes, like we explained before. We have also announced prizes for most compelling DeFi and NFT focused project, along with prizes for 4 runner-ups. If you have any queries, you can always reach out to us on our sponsor channel on ETH Online, or join our Discord channel. To learn more about what we do, check out our website. Do give us a follow on Twitter too. Happy hacking!